Saxon Advanced Mathematics, Lesson 32. We got a barn burner, ladies. Let's dive in and see if we can make sense of this. The first topic is kind of just a preview. We're going to talk about inverse functions. Let's say that we have a function, 2x minus 1, and we're going to put some values into that function. Let's say that we're going to choose for our independent variables of x 2, 4, and 6, and then, or this is our domain, right? And then we would generate a range. Let's calculate them. 2 into this would be 4 minus 1 is 3. 4 into this would be 8 minus 1 is 7. 12 minus 1 is 11. Okay, so this is a function. We have a one-to-one mapping between our independent variables and our dependent variables, our domain and our range. Everything's in order. It looks good. But what if we wanted to find the function that would let us go from these numbers to these numbers? That's what's called an inverse function. Okay, it will allow us to take these numbers, and you know what, I won't even do it like this. We want to put them here. We want to be able to put in 3, 7, 11. And we want to get out 2, 4, and 6. So how do we create the function that's going to allow us to go backwards? Right here, I'll do this here just to make it as fun as possible. Here's the rule for how that we do that. We solve, let me bump this up. We solve the original equation for x, whoops, not Fox, for x, and then we replace x with y and y with x. 2 steps. Okay? This is to find an inverse function. Okay? So again, inverse functions allow you to move in the opposite direction. If you're moving this way, it allows you to take those answers and move back the other way. This idea is going to be important to us in the later part of this lesson. So let's take our inverse function here, which was y equals 2x minus 1. Okay, so we want to solve the original equation for x. All right, let's add 1 to both sides. And we'll get y plus 1 equals 2x. And then we'll divide everything by 2. And now I'm going to just reverse it. And I'll get x equals I'm going to write this as 1/2 y plus 1/2. See, I'm just pulling this apart to write it as 2 separate pieces. And so now it's solved for y. So this was step 1. And now I'm going to do step 2. I'm just going to swap these out. And it's going to be y equals 1/2 x plus 1/2. So what that means is that this should work to go in this direction. Let's see. 3 times 1/2 is 3 halves. Plus 1/2 is 4 halves, which is 2. That one works. 7 times 1/2, that's 7 halves. Plus 1 more is 8 halves. That's 4. That one works. 11 over 2 plus 1 more is 12 over 2. That's 6. Okay, so it worked. That's the reciprocal function. It's quite straightforward. As long as you know this process, Solve for x and then flip the letters around. As long as you can remember that, these are a piece of cake. Let me flip, and we're going to do a couple more of these just to practice. But I want to show you, let's just do one more, and then I'll show you the picture. There's a cool graphing thing that happens. 32.1, that was like a non-example. Find the inverse function of y equals 2x plus 3. Okay, so our steps are number 1, solve for x. Okay, so I'm going to subtract the 3, and this time I'm going to flip the sides right away because I want my 2x to be on the left because that makes me feel better. So I'm going to move the 2x over equals y, and then it'll be minus 3, right? Because it would be like that. Okay, so 2x equals y minus 3. I'll divide everything by 2. Last time I showed it as 1. It works better, I think, to look at it like this. That cancels, and then I'm going to flip the letters. Okay, so this x has now become a y. I'm going to write this as 1/2, and that becomes an x minus 3/2. And that is the inverse function. It will allow us to go in the opposite direction. And this is what I wanted to show you. What's kind of cool if you graph them. And John is not asking us to graph them, but he's being kind enough to do it. If you graph the original function and then the inverse function, they have a line of symmetry that goes between them. What? Isn't that cool? How that creates it? We'll look at the other one when we finish it. He's not asking us to graph, but he is showing us that nifty relationship. Example 32.2. Find the inverse function of y equals minus 2x plus 5. All right. 1. Solve for x. So I'm going to subtract 5 from both sides, and I'm going to flip it. That will give me minus 2x equals y minus 5. Divide by minus 2. And I'll simplify this time because I've got a lot going on here. It'll be x equals minus 1/2 y plus 5 over 2. Lots of drama with the signs. And then 2, flip the letters. That's my shorthand for the long step. So I'll get y equals minus 1/2 x plus 5 over 2. That is correct. And, oh, I know what I wanted to tell you. It isn't just that this is the line that goes in the middle of them. It's that y equals x is the line of symmetry that both of these will find themselves on. And this one that we just did is kind of weird. Here's y equals x, it's the line of symmetry. And look, they cross like that. So they're still symmetrical, but it looks really different, doesn't it? So fun things happen when you graph inverse functions. That's what I want you for the takeaway. Again, John's not asking you to do that, but you can. Okay. Now, let's take this and march into the land of trig functions, okay? Now, last time we talked about the fact that trig functions have signs in different quadrants. They have different values, and that's going to be useful in what we're talking about now. What I'm going to do is I'm going to summarize that quickie little way to remember it chart that I did last time. Sine, cosine, tangent are all positive in the first quadrant. Over here, there's this fun pattern, right, where it goes plus, minus, minus, and then minus, minus, plus, and then this one is minus, plus, minus, right? And we're doing, all of these are in the same order, sine, cosine, and tangent. If we wanted, Oh, and let me just put the degrees on here. This is 0 degrees. This is 90. This is 180. This is 270. But we can also call this one minus 90, can't we? We can measure it as a negative. All right. So let's look at cosine and tangent first. If we wanted to come up with a range of values, angle values, that would allow us to get every positive or negative cosine value, we could do that like this, couldn't we? Between the first quadrant and the second quadrant, cosine goes from positive to negative, right? And so we can say that between 0 and 180 degrees, we get the full range of all the cosine values because we've got positive and negative, and it goes all the way from one extreme to the other. The same is true for tangent. Between the first quadrant and the second quadrant, we've got all the range of positive and negative values, and so we can say that between 0 and 180, we've got all the values of tangent we need. Now notice down here, they're mixed. We have more negatives and more positives and more negatives, but we've already got all the values up here. This is just repeats of them. Notice with sine, it doesn't work out quite the same way because sine is positive over here. So in order to get a full range of sine's values, we have to go down. Now, we could go over here, right? Because here's negative signs, but we're trying to keep this simple. So we went across for these, but for sine, we have to go down. Now we get 1 plus 4, right? Those are the quadrants that we're using. And it's ranging from 90 degrees to minus 90 degrees. I'm going to make that an arrow so it's not confusing. All right, this is going to be important what we get to next. But what I'm trying to do is I'm trying to really simply define a range for each function that will allow me to get all the positives and all the negatives with just a really simple range of values. This is going to be helpful to us, so keep that in mind, okay? Now, let's talk about the inverse function of these, and we're going to go in this same order. We're going to talk about cosine, then tangent, and then sine, for the very reasons that I'm describing here. Cosine and tangent use the same range, and then sine has to go in a slightly different direction, all right? So, John's got tons of information in here, and I'm trying to keep it as simple as possible. Okay, so let's talk about inverse cosine first. All right, so what we can say, here's a triangle. Let's put in a familiar friend. Let's put in our 30, 60, 90. Here's the 60 degrees right here. So we know if this is the 60 here, I'll draw it like this so we can see our friend. This is the 60, 30. It's 1, 2, square root of 3, right? So that means this is 1, and this is 2. And this is square root of 3. If we want to find the inverse cosine, cosine usually is based on the degree, right? And then we get a ratio. And we would say the cosine of 60 degrees equals, cosine is adjacent over hypotenuse, right? So it would be 1/2. What we can say is the inverse function, and there's two ways we can write them, and this seems really random. Arc cosine. This just means inverse. What? Why would they use that word to mean inverse? I don't know the backstory on that, but this simply means, this prefix means it's the inverse of the cosine function. We can also write it the way it shows up on your calculator, which is with the -1, but we're gonna rely more heavily on the arc cosine, okay? We don't say arc cos, we say arc cosine. We say inverse cosine, I think is the best way. This also works as well. Both of these mean the inverse function of cosine. And we would say the inverse cosine of 1/2 equals 60 degrees. So we're using the very same information. We're just presenting it in the opposite form, just like we did back here where we were doing inverse functions, right? We just want to go in the opposite direction. And so we need to give that a name so we know what we're talking about. So we can create inverse functions for our trig functions using either of these two notations. Here, let me just scooch up so you can see a little better. This or this. Now, the only problem with this is that there are a lot of triangles that would relate to this. Let me show you what I mean in the book. Here's what I drew, right? And we say the arc cosine, or the inverse cosine of 1/2 equals 60 degrees. We took the ratio, or it could be a decimal number, but we took the ratio and we wanted to find the degrees. That's what inverse cosine does. We've been using that on calculators. The problem is that because we can, this is a 60-degree angle, but what if we wanted to say it's a 420-degree angle? Well, that would give us the very same triangle, wouldn't it? Because we'd go around once for fun, and then we'd go another 60 degrees. What about a 780-degree triangle? That would be going around twice for fun, and then 60 degrees. And so there are an infinite number of degree measurements that will reflect this same triangle, and somehow we have to limit that because we don't want to be listing out all of these degree measurements as the answers for our inverse cosine problems. So we have to come up, so mathematicians came up with a clever way to limit this. And what they did was, instead of writing this word like this, they put in an uppercase A. And if you choose this format, they use an uppercase C. Okay, so I've changed both of them by using uppercases. And what this does is it says, hey, we're not just gonna keep spinning around and making new triangles by going in circles forever. We're gonna use limits. And the limits are what we talked about up here. So when we're calculating the degree measurement of an inverse function for cosine, we only have to consider angles between 0 and 180. That's going to keep us from having to spin around in circles like that and come up with an infinite number of angles that would also match our answer. We're limiting it and saying, no, just what's between 0 and 180. That's all. Okay, so this is a super helpful technique that simplifies our answers for us. Okay, this is a lot, I know. We're going to work on it, and what you'll find is that this actually makes a whole lot of sense once it settles into your brain a little bit. It's not harder. We're using all our same information. We're just learning to work in the opposite order, and because that creates that weird spin around problem, we're putting some simple limits on it. Okay, so when we use an uppercase here or an uppercase here, we'll use mostly this one. What we're saying is find out all of the angles that will have a cosine of 1/2, but you only have to consider the angles between 0 and 180. When we get into the problems, you'll see that's a big help. Okay, when we do inverse tangent, we're going to put the same limit on it because tangent is using the same limit between 0 and 180. Is there anything more I want to see about tangent? No, we're going to do the same thing with all of them. We're going to put limits on them. These are the limits that we'll use. Okay, so this is super important to remember this and to understand why. We'll keep talking about it as we go, so don't worry. I don't expect you to remember forever now. Inverse, and I want to kind of cut through this drama and get to the problems. Inverse tangent has the same situation where we can say the inverse function is arctangent or like this, but that would create all those angles and we'd have a million answers. So instead we use this and that. To make it simple, the limits on this are 0 to 180 as we showed on the other page. Another thing that's going to be super helpful for us to remember from here on out is that we can always find tangent by doing over Arthur, but we can also do it by doing sine over cosine. This is a great shortcut when we've already calculated these. It just is a quickie way to do it. All right, and then inverse sine, we use the same abbreviations. Instead of saying arc sine like that, we put the uppercase A on it to show that we want to put limits on it. Same thing with the sine, we use an uppercase S. But these limits go from 90 to minus 90. You can think of it that way. Some people think of it as minus 90 to positive 90, whatever sticks in your head better. But the limits for sine are different, and it all boils down to which quadrants they're positive and negative, okay? So if this will eventually soak into your brain, it'll help you remember these limits really well, because you'll go, oh yeah, cosine and tangent go positive and negative this way, but sine's positive in the second quarter, so we have to go find his negatives down here. All right, let's work some problems and see if we can figure this out. Here comes the fun part. All right, and P.S. we have 1, 2, 3 more problems, 4 more problems, and then we're done. Example, gee guys, only 4 more problems. Evaluate, we want the inverse function of sine, the inverse sine of that, okay? We recognize that it is an inverse function not only by its name, but by the shape of the answer, right? Usually when we have trig functions, we have a degree measurement in front of them. This one, we have the ratio of the sides, and we're looking for the degree. Okay, so we're going in that opposite order, just like at the beginning when we did the function backwards. Now, what happened though is that we see this looks pretty familiar. We're kind of familiar with these numbers from our reference triangles, which we'll be using in these. But we can see, oh, somebody rationalized this denominator, and that kind of messed up the numbers and made it look less familiar. So what we're going to do is we're going to unrationalize the answer. So we're going to multiply by that. That will give us 2 over 2 times the square root of 2. Then this will cancel. And then we'll get 1 over square root of 2. Now I'm vibing my reference triangle really hard, right? So I'm ready to start drawing it. I can see this is 45, 45, 90 territory right here, right? And it's sine, so I know that my choices are either the first quadrant or the fourth quadrant. Which quadrant does this triangle belong in? Well, it's positive, so that tells me it's first quadrant, right? Because that's where I have the positive values of sine. So I'm going to draw a 45, 45, 90 degree triangle right there. And I know it's 1 square root of 2. I know that this will be 45 degrees, so if everything looks right, this would be Oscar had, right? So opposite over hypotenuse, that's right. So that tells me that the arc sine of square root of 2 over 2, to go back to the original problem, equals 45 degrees. We went from the decimal number, which in this case, when it's in our calculators, we express it as a decimal when we did inverse functions in our calculators. Here we're expressing it as a fraction, but we're going from the ratio of the sides to the degrees rather than, we can also say, right, the sine of 45 degrees equals square root of 2 over 2, right? So that's how we see that these are inverse functions. This is the answer to this problem. That's all there is to it. That's not so bad, right? Okay, let's do another one. It makes a lot more sense, I think, when you see it in a problem. Okay, evaluate arc tangent. I see that I've got the uppercase A. That makes me happy. It tells me I only have to look at 2 quadrants. I don't have to spin around and keep adding 360 to come up with a million angles that would all have these same triangles. But this is what it is. It's minus 1 over 3 times the square root of 3. Messy. Okay, again, I go, this looks like a rationalized triangle. I want to simplify this because I think that it's going to fit into one of my reference triangles. P.S. Spoilers, they all do. But I need to make this look more familiar. So I'm going to, once again, I'm going to de-rationalize by multiplying by this. That's going to give me 3 on the top, and it's going to give me 3 times the square root of 3 on the bottom. Those cancel, and I get 1 over square root of 3. That is definitely 30, 60, 90 territory, right? So let me draw that reference triangle and get my bearings. This is my 60 degree. This is my 30. There's my corner. It's a little wonky. This is the 2. This is the 1. This is the square root of 3. Okay? So the question is, how do I orient my triangle in my drawing? It's tangent, so that means this is over Arthur. That's more helpful for me in this case than looking at sine and cosine, because I haven't calculated those. So if I haven't calculated sine and cosine, I'm just going to go to this. I want the opposite side to be 1 and the adjacent side to be square root of 3. Okay, that's cool. That means I want to be in this angle. That's my point of reference, because that gets these lined up for me properly. I know it's not the 60 degree. But I got to pay attention to that too. I want it to be minus. Well, tangent, I know that the limits for tangent are 0 to 180. And I know that if this is the quadrants, it's positive here and it's negative here. So that means this needs to be a 4th quarter angle, doesn't it? It needs to be like this. Well, that might not be quite right, but I want the 30 degrees here so that I will have the square root of 3 here and the 1 there and the 2 there, and then this gives me opposite of 1 adjacent of square root of 3. Check, that's what I want. So this is, so I can write the whole thing over again, the arc tangent of minus 1/3 times the square root of 3 equals minus 30 degrees, or I could say 330 positive degrees, right? Either of those answers is acceptable. John and I both prefer this one because it's a more, it's a simpler, more direct answer. This is the same thing, but it just is a clumsier number. All right? Okay. 2 more. This one may blow your mind a little bit, but it's okay. Just work with me. 32.5. Evaluate. We want to find the cosine of the arctangent, in case A, good, that means limits, of minus 3/5. What in the world? Okay, but let's just go slow and figure it out. The first thing we need to do is draw the triangle, okay? This we can see by the numbers. This does not look like one of our old friends. We know it's tangent, so that means our limits are 0 to 180. That wasn't right. Oh no, it was right. Take a break for a second. What I'm thinking about, you guys, is that I told you that tangent is evaluated between 0 and 180 degrees back here. Remember this? But then I drew my negative inverse tangent function in the fourth quadrant, where it is negative. But why did I do that instead of drawing it in the second quadrant? It's still the right answer, but it's not consistent with what I told you here. Now, John did exactly what I did, and so I have to stop and look at that and figure it out. Why we used the fourth quadrant here instead of the second quadrant. So let me come back to that. But in this one, we're going to use the fourth quadrant again. Okay? So we know that's true because if we look at our signs of our trig functions, we know those are all positive. We know it goes positive, negative, 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 positive. And then it goes like that, right? So, I could have just looked here. I said that we wanted to look at tangent between first and second, but now John is using first and fourth for tangent as well. So he's saying use these limits for tangent, which makes it like sine. Now, what I have to say about that is either one would make sense, right? As long as we're getting a limit that includes the positive and negative values of tangent. Wait, I circled the wrong one. I circled the wrong sign number 2. You guys, I want to cry. I want to just delete this whole video and start over, but I'm not going to do that. Let me rewrite the numbers. Are you crying? Okay, for cosine, we definitely want to go this way. Cosine, we want the limits to be from 0 to 180. Sine, I had the right quadrants, but I circled the wrong number. It should be this and this, because this is sine, right? That should be, that's the right range. And then for tangent, John's now saying, let's go down and do this, okay? So the important thing is that we are combining positive and negative quadrants so that we get the full range, all right? So let's use tangent as positive 90 to negative 90 and stick with that plan. All right, so we've resolved this. We're just using the fourth quadrant for tangent, which is fine because that gives us positive and negative. Okay, now I'm gonna try to do this problem and not confuse you further. Don't worry, we're gonna be working on these for quite a while, so we'll have more time to get used to it. Okay, tangent is negative. That means it's in the fourth quarter. The opposite over the adjacent, okay? So that means we have a triangle that looks something like this. Whoops, pretend it's perfect. The opposite side is 3, and the adjacent side is 5. Now, we don't know the degree measurement, and short of using our calculators, we don't have any way to find that degree measurement. But John isn't asking us to find the degree measurement. He's saying, once you identify the triangle, find cosine of that. Cosine is Oscar had a hold. So he's saying, figure out this triangle, use this information to figure out a triangle, then tell us adjacent over the hypotenuse. Well, we've got the adjacent, right? And we've got the opposite. How are we going to find the hypotenuse? Pythagorean. Because a squared plus this squared equals that. So if we mentally rearrange it, we can take the square root of 5 squared plus 3 squared. Dig it? We'll never know this degree measurement, but we don't need it. We can go from the sides to the triangle to the sides we need for that. So h equals the square root of, this is 25, and this is 9. And so that is the square root of 34. That's this. And so to find the cosine of this, we want the adjacent over the hypotenuse. The adjacent is 5. The hypotenuse is square root of 34. All right. Now we need to just rationalize this. Let me bring it down here so you can see. 5 times the square root of 34. We rationalize it. And our final answer to all of this is 5 times the square root of 34 over 34. We can't simplify that. It's 17 times 2. We can't simplify here. That's our final answer. And this is 5. Yes, that's correct. All right. And then our last problem, example 32.6. Evaluate the sine of the arc cosine, or the inverse cosine, of 2 over 3. Okay, so again, we see what we're going to be doing here is we're going to draw the triangle as best we can, get these sides in, and then figure out what sides we need to calculate sine. We're never going to get the degree measurement of any angles. We could if we used our calculators, but we're not going to do that. We're just going to skip ahead. So cosine is positive in the second quadrant, right? So the new limits we're using are sine goes from 90 to negative 90. Cosine goes from 0 to 180. This is first and fourth quadrants. This is first and second quadrants. And tangent, sorry for all my confusion. We're going to let tangent chill with sine, and he'll be 0 to minus 90, first and fourth. Okay? I'm sorry for all that confusion. I feel bad. If it wasn't a million hours long, I would re-tape the whole darn video. Okay, but mistakes happen, you guys. Mistakes happen, and it's okay. So this is cosine. It's positive, so that tells me it's first quadrant. I can tell by these ratios that it's not one of our predictable triangles because none of them have a 2 and a 3 in the same triangle. 30, 60, 90 has a 2, but it has square root of 3. So there's no way this relates to that. So I'm going to remember cosine is a hold. I'm going to draw a triangle, and I'm going to make the adjacent side 2 and the hypotenuse 3. This is the opposite side. This is adjacent. This is hypotenuse. This is the opposite. I don't know it, but again, I can use Pythagorean to solve. This I have to be careful though, because this time I have the hypotenuse and I don't have these. So I'm gonna say O squared over opposite plus 2 squared equals 3 squared. This is 4, this is 9. I'm gonna subtract the, I'm trying to do it in too many steps. There. The opposite side squared plus 4 equals 9. I'm going to subtract 4. And I'm going to get the opposite side equals the square root of 5, right? Now I can find my sine. Sine is equal to Oscar had, right? This relates to this. So again, what I'm doing is I'm using this information to create part of the triangle. I'm using Pythagorean theorem to find the third part of the triangle, side. And then I'm following this instruction to gather up the information I need to find that ratio. And sine is opposite over hypotenuse, so it's square root of 5 over 3. That's the final answer. I hope this is not making you crazy. If not, if it is, we can talk about it in the video. I apologize profusely. I hope that you see that this is kind of fun to fool around with these because it's like a big crazy riddle that you can resolve without having to resort to a bunch of long calculations or calculators. No formula. Well, there's formulas. Yeah, that's true. Okay. We can also talk about the spinning thing if that's confusing you. But the bottom line is that this uppercase letter says let's put limits on the quadrants we even have to worry about, and it just makes our lives so much simpler. That is 32. It is in the books. Thank you. See you next time.